Alright, hey guys, this is going to be 2.10, inverses of exponential functions. So last topic was writing equivalent forms from exponential to logs. Now we actually want to use logarithms themselves to find the inverses of a given exponential. So let's talk about the general form of a logarithmic function. We have f of x is equals to a log base b of x, where x is the input. And let's refine some of these rules a little bit better. It says where b is greater than 0 and b cannot be equals to 1. That is true. It will create an invalid log. However, a here can be equals to 1. This is not exactly a correct statement. To refine this, I'll say a cannot be equals to 0. Because if you think about it, if a was 0, it really wouldn't be a log anymore, right? So we probably don't want it to be 0. Okay, so you can take some time to read this if you'd like. But for the most part, I should be able to hit the keynotes here if we just kind of look at these tables. So for exponential functions, if we look at any particular table that defines an exponential, the input values will always be added by the same amount. Whether it's 1, 2, or 3, it just adds the same amount each time. And as we observe the behavior of the output values, they will always multiply by the same factor each time to get from one number to the next. Right? That's what defines an exponential. Now, if I want to know the behavior that defines a logarithm, just switch it, right? If we know that the rules for inverses is just switching x and y, the rule should also switch. So as we observe a table here for this logarithmic function, the x values are now multiplying by 2, and then the output values are adding by the same amount. So basically, in my head, how I try to keep track of this is that exponential is an add multiplies type of behavior for a given table, and then logarithmic is just simply the opposite. It's going to be a multiply adds. Okay, multiply adds. All right. So just using that idea itself, we should be able to figure out whether or not these tables given to us in example number 1 is either logarithmic or exponential. So let's observe the behaviors of the inputs and output values. The input values are adding by 1 each time. My output values are multiplying by 1/2 each time, which should indicate add multiplies, which I infer to be an exponential function. Taking a look at the second table, the x values are multiplying by 3 each time, and my output values are adding by 10 each time. This is multiply adds, which infers that this is logarithmic. Here's the third table. If I can scroll to it at some point. All right, here we go. So the input values are multiplying by 10 each time. And then if you notice for the output values, if you attempted to say that they're adding the same amount each time, you would quickly find out they are not adding by the same amount each time. Instead, you might rather infer that, hey, it looks like they are multiplying by 2 each time, which doesn't really follow any of the patterns that we were talking about prior. Either it's going to be add multiplies to be exponential, or multiply adds to be logarithmic. This is multiply multiplies. And we haven't really covered this behavior yet, but this is a good to know, but I need to know. This type of function is a power function. Right? If you ever see behavior like this, is a power function, where a power function has this particular parent function, a times x to the power of b, where this time the base of this exponential is the dependent variable. Right? Not a need to know, but good to know. And here's our last table. My input values are multiplying by 2 each time, and then my output values are subtracting by 3 each time. So even though we're subtracting, the rule still stands. I'm just adding by a negative number, so this is still very much multiply adds, which means this is logarithmic. All right, let's continue. All right, we've already kind of covered inverses in general with this particular fact right here, so we can revisit it again and see how it also works with exponential and logs, right? If we ever do composition of one function of the other, and one or the other composed of the original one, and the result is x, then we can claim that the two functions are inverses of each other. Let's go ahead and prove this fact for example number 2, right? They have given us two functions. I'll highlight the first one in blue. I'll highlight the second one in red. and we'll perform f composed of g of x. Right, the first statement here. Let's take f, and then we'll compose it with g. So I'll first start off by writing what f is. It is 3 to the power of x. And I'm not going to write in x right now. I could, but really I'm about to change that x into the g function. So we'll plug in the g function into that x and write log base 3 inside the exponent. Now, if you recall from the previous video or the previous notes in 2.9, if you ever have a base and the exponent of a log, if you have a base and the exponent is a log with the same base, the result is simply the input of that log. So this is going to be all equals to x. Alright, let's do g composed of f of x. I'll start off by writing my red function, log base 3 of x. But in this case, the input is no longer x. We want to plug in the other function, 3 to the power of x. And then here we're going to recall a previous property as well. If you have the base of your log and the base of the input is the same, then the result is simply the exponent of your input. So this is equals to x. Now that we've proven both cases, we can now claim that f and g are inverses. Alright, let's continue. Before we continue, let's go and just do a quick recall here. I skipped this for a reason, right? The main idea here is that whenever we graph inverse functions at all, the reflections of each function, the inverse and the original, will always reflect across the y equals x line. You can see that's true really quickly. Let's say I had some quadratic here. The inverse will be some square root function that looks like this, right? They will reflect across that line. And if I wanted to do this by hand at any point, I can always just take any particular x and y coordinate of the original function and then switch them to find the new graph of the inverse function. All right, that's all they're saying there. We're going to apply that second statement to example number 3. They have given us an original function of k of x is equal to 2 to the power of x. Let's find some nice points. And then we'll just switch the x and y coordinates for these points to graph the inverse function. So I'm going to start labeling each of my points. -1, 1/2, 0, 1, 1, 2, and then 2, 4. So as long as I switch every x and y coordinate, I should produce the inverse function. For this first point here, I'll say 1/2 -1, which is down here. 0, 1 is now 1, 0. 1, 2 is now 2, 1. 2, 4 is now 4, 2. So there's my new points that draw the inverse graph. And so as long as I connect my lines, like so, I have now drawn the inverse. And you can clearly see now that yes, this does reflect across this y equals x line. And also I also want to mention that recall that exponential functions, this original function here, has a horizontal asymptote at 0, which means that I would have a vertical asymptote at 0 now for any given log. Alright. Let's do example number 4. The exponential function h of x is equals to a to the power of x, contains the points 2, 3, and 6, 27. Find the average rate of change of y is equals to log base a of x over the intervals 3 to 27. So all they're saying here, I would specify this a little bit better. This will be h inverse of x here. They're kind of wanting us to find the inverses average rate of change, since we're going from an exponential here into log, right? So there's my inference there. And so we kind of just want to be mindful of what points were given to us and see how we can use that to convert it to the inverses, right? So they have given us points from the original. If I switch the x and y values, I now have the new coordinates that belong to my inverse function. And I'll use this to help me find the average rate of change. Recall that the average rate of change formula, in this case, we're doing the inverses, so it'll be h inverse of x2 minus h inverse of x1, all divided by x2 minus x1, right? Change in y over change in x, if you heard that before. So I'll plug in what I know. And in this case, for the inverses, x1 and x2, and this is the y1, y2, I'll plug in what I know into my formula. I now have 6 minus 2 over 27 minus 3. And if I simplify this, I get 4 over 24, which is equals to 1 over 6. Alright, let's continue. Here's a lot of key information here. I'm just going to hit the highlights. We've already covered what a general form is. Here's a domain and range of our parent function. The only one that's going to change based on a log function is the domain. So depending on any horizontal translations, this domain may change. Range will always be negative infinity to infinity. So here, just like exponentials, depending on the a value, it will either indicate growth or decay. Here is when a is greater than 0. You can see that it's increasing. Here, when a is less than 0, the graph of a log will look kind of like a decay here where it's decreasing like this. And similarly to exponentials, it will either always be increasing or decreasing in nature, as well as either concave up or concave down. Never one over the other, right? So it's either increasing or only decreasing, or concave up or just concave down. Not one or the other. And then end behavior-wise, now that we have a vertical asymptote to deal with, 1 second, my iPad is lagging. Let me pause real quick. All right, we are back. It should be working. All right, nice. So now the end behavior will be slightly different as far as the limit statement goes, because now that we have a vertical asymptote for any given log function, the parent function is x equals 0, of course, right? We can only approach 0 from the positive side. Before this limit notation, we usually said negative infinity. We now can't say that since there is a vertical asymptote in the way. So depending on where that is, that will affect the limit statements. Majority of the times it should be 0. Other than that, these are the only 2 limit statements that you should be able to write for any given log. Let's go ahead and practice that skill right now. For this particular graph, they already started off by writing the left limit statement. As x approaches 0 from the positive side, the function is going down towards negative infinity. The limit, as x goes to infinity, f of x is going to positive infinity as well, at a pretty steady rate. Here's part B. The limit, as x approaches 0 from the positive side. Again, we're referencing that they're approaching this asymptote here. The limit, sorry, not the limit, the function now is approaching infinity. The right limit statement, the limit as x approaches infinity, f of x is going down towards negative infinity. And here part C, they were not nice to us. They did not give us the graph. However, we can assume the general sketch of what this graph should look like based on the a value. Since the a value is bigger than 0, I'm referencing this previous information here. In my head, this is what I should be sketching. So, in theory, my graph should look like a growth log. Knowing that now, I can write my left and right limit statements more confidently. That the limit as x approaches 0 from the positive side, f of x is equals to negative infinity. And the limit as x approaches infinity, f of x is also going towards infinity. Alright. That's it for its limit statements. Let's go ahead and cover, oops, I forgot to erase this. Spoiler, let me erase some stuff here in case I forgot to erase them. I did, yeah. Alright, cool. Alright, so you've already saw the answers, no big deal. I'm just going to quickly walk through it again. They're very quick though. So for sure, this graph shown is concave up and decreasing in nature. Again, not decreasing slope, but decreasing function, right? Here I'm concave down, but increasing function. Part C, we have to kind of sketch what this looks like based on the a value there. So that should be a decay log. So starts up here and goes down. So that's concave up and decreasing. All right, now let's move on to these tables. All right. So selected values of the several log functions are shown in the tables below. For each table, find the values of the constant k. So since I know the behavior for any given log, it's multiply adds. As long as I find the multiplicative factor, I should be able to figure out exactly what k is. So to get from 1 to 2, I should multiply by 2. From 2 to k, I should also multiply by 2. And you can also see that from 8 to 16, I'm multiplying by 2. So if I had to assume what k is, k should be equals to 4. This next table, they're given the k as the first option here, so we might have to look at the behavior of the numbers following it. So from 6 to 18, I'll multiply by 3. The 18 to 54, I'll multiply by 3. And it seems to work out for every single value here. So if I want to go back, just divide by 3. So we'll take 6 here, divide by 3 to get to k. K should be equals to 2. Alright, here's part C. Now this table might be kind of tricky, because if we look at the input values, there's really no clear-cut pattern in terms of multiplicativeness from one number to the next. It seems like instead, it's adding by 1, then adding by 2, then possibly adding by 3, but if we tried this, this won't work. Let's say we assume this did work. 7 plus 3 will give me 10. And if I keep going down this additive pattern, I would say plus 4 here, and 10 plus 4 does not give me 19. So that doesn't quite seem to work. Instead, what's happening in terms of this is that we can find the multiplicative behavior amongst the first difference. In this case, I'm multiplying by 2 to get one additive number to the next. So from 1 to 2, I'll multiply by 2 again to get plus 4 here. So 7 plus 4, we're assuming k is equals to 11. We'll multiply by 2 again and add by 8. And see that 11 plus 8 does give me 19. So again, the takeaway from this problem is that the multiplicative nature can be found within the first difference. Alrighty. So for sure, that k is equals to 11. Last table here. I'm noticing that we are adding, or we're multiplying by e to add the exponent from one term to the next. So for example, to get from e to the negative 2 to e, I'll multiply by e to the power of 3. Right? So the exponents add to be 1. And so it seems like this will happen throughout all the numbers here as far as the inputs goes. Right? From e to the power of 7, I would also multiply by e to the power of 3. Which indicates that to get to k, I'll multiply by e to the power of 3 there. And so e times e to the power of 3 will infer that k is equals to e to the power of 4. Alright, that's it for example number 3. Let's wrap up with domain and range for any given log function. So again, recall that range for any given log will always be negative infinity to infinity. There is no need to think about this at all. It will never be affected or changed by any particular transformation. Now, domain though will vary depending on any horizontal translation. Notice here that there is no horizontal translation. If you really want to make a sketch of this, you can imagine that this is true because this is a growth log. It has not shifted left or right at all. So domain is 0 to infinity. Here's this one. I've now noticed that this is going to be a log with an a value less than 0. It indicates a decay log, and it's also shifted right by 3. And so hypothetically, I'm moving this to the right by 3. And since I moved it over by 3, that means my vertical asymptote that was at 0 also moves over by 3. And so now if I look at my domain, it should really be from 3 to infinity. And then one last one. Here, we just gotta make sure to notice that, hey, there is something in front of my x, and I should probably factor that out. So if I rewrite this, I should have 8 log of 2 times x plus 3 over 2. Now that I factored it completely, I can see a horizontal translation left by 3 halves, which means figuratively the graph itself here is moving to the left by about 1.5 units. So right about there, we have a vertical asymptote at x equals negative 1/2, which infers that my domain is from negative 1/2 to infinity. All right, that's the last bit of 2.10 here, or sorry, 2.9? 2.10, and 11 actually. So that's it. Go and watch 2.12 now. Bye.